Okay, let's get started then. Yeah, I'd just like to welcome everybody to the Rochester section of the OSA, our Tuesday night tech talks. And I'd also like to welcome, we've also invited the New England section of the OSA, so welcome everybody. And I know Don got some good publicity for this, so there was a news article about this, so welcome all of our guests here tonight. Before we begin, I just want to mention that during the presentation, if you don't mind just muting your microphone, afterwards we can have more of an informal Q&A. If you'd like to ask a question, you can raise your hand, or if you'd like to just jump in and ask a question, please feel free to do that afterwards. So tonight you'll be hearing from Dr. Don Feiger and Justin Gallagher. And I'll give a brief introduction here to Don, who is the director of the Center for Detectors and the Future Photon Initiative, as well as a professor in the College of Science at the Rochester Institute of Technology. So he researches massive star clusters, the galactic center, and advanced detectors for cross-disciplinary applications. He has developed detectors and instruments for the Hubble Space Telescope, the James Webb Space Telescope, and those used in the Nobel Prize winning research that discovered dark energy and the supermassive black hole at the center of the galaxy. So he continues to develop infrared detectors and single photon detectors for astrophysics and quantum information science. And Justin Gallagher is also joining us today. And congratulations, Justin, who graduated this year with his master's in, correct me if I'm wrong, the astrophysical sciences and technologies. Great. So without further ado, I'll hand it off over to Don, and please feel free to share your screen.
Okay, can everyone see that?
Yes, we're not seeing the presentation mode yet.
Okay.
We can see your screen.
I see the first page of the presentation.
Uh-huh.
So
There you go.
there you
Perfect.
go.
Good.
We're up.
Okay, well, thanks. It's a pleasure to be here virtually. I wish I could see you all in person. And Chris, thanks for inviting me to give this talk. I don't think he said it, but Chris was a student of mine when he was at RIT. And he contacted me maybe a month ago to ask me if I wanted to give a talk. And it was very timely. I was very excited at the time. I'm still excited, but I was excited because the Nobel Prize was awarded in physics to something that was close to my own research, and I had some participation in it. And I remember on October 5th, which is my birthday, going to sleep and asking the question, when I wake up in the morning, will the supermassive black hole in the galactic center get the Nobel Prize? Now, you might think that I'm really good at predicting the future if I actually thought that. But I'd been thinking that every night before the Nobel Prize announcement for the past 10 years. So it just so happened to happen this year. And so what I wanted to do was I wanted to tell you a bit about the story of the Nobel Prize and also relate how instrumentation was the real key enabler for making it possible to do the experiment that led to the Nobel Prize. And in fact, the experiment itself conceptually is very simple. So here's the official cartoon that the Royal Swedish Academy of Sciences put out when they award a Nobel Prize. And these are the three recipients. One of the rules, evidently, of the Nobel Prize is that no more than 3 people can win the Nobel Prize. And here are the winners this year. Sir Roger Penrose won half of it, even though he's 1/3 of the contingent. He won half of the award. And he won that for theoretical work he did in the 60s, showing that general relativity was consistent with the singularity of a black hole. So his was a theoretical piece of work. And then over on the right, you can see 2 other people, Reinhard Genzel and Andrea Ghez, and they split the other half of the prize. And that's for an experiment they did. So it wasn't theoretical at all. Rather, they did an experiment that convincingly showed that there's a supermassive black hole in the center of our galaxy. So I'm going to provide a little historical context, explain how to measure the mass of the black hole, describe the actual experiment that led to the Nobel Prize. I'm going to take a little personal digression for some work I was doing at the time related to the work that got the Nobel Prize. And then I'm going to talk about the three major technologies that really made this possible. So it's big telescopes, adaptive optics, and infrared detectors. And I'll explain to you why those were important, because there are very specific reasons why they're important. Another technology, if you want to call it that, would be sophisticated one-of-a-kind instruments that have to be built from scratch. And teams of astrophysicists build those instruments. So I'm going to describe some of that. And then I'm going to ask Justin to finish by describing some future detector technologies that we're developing at RIT in the Center for Detectors. So first, some historical context. So about 100 years ago, I guess 90 years ago, Carl Jansky built an antenna, and he used it to make the first radio observations ever. So this is at centimeter wavelengths. And one of the things he noticed was that there was a blip in the signal every 23 hours and 56 minutes. And that's the rotational period of the Earth. And so what he found out is there's something out in space that emits a lot of radio energy, and it goes across the same point in the sky above his radio telescope once a day. And that was located in Sagittarius. And because it was the brightest radio object in Sagittarius, it was called Sagittarius A, or Sag A. And the second brightest peak in Sagittarius is called Sag B, and Sag C, and Sag D, etc. So Sag A was thought to be at the center of the galaxy. So fast forward into the late 60s, Eric Becklin and his thesis advisor, Gary Neugebauer, discovered the galactic center in the infrared wavelengths. So this is about 2 microns. There's an interesting story there. One night, Eric was going to go out, and Gary asked him where he was going, and Eric said, "I'm going to go discover the galactic center." And Gary said, "Well, it's not there. I already checked." The problem was Gary looked for the galactic center using radio coordinates on the previous radio coordinate system. Radio coordinates have 2 systems, and they were changed at some point. And so the lesson there is never get coordinates from a radio observer, radio astronomer. So Eric went out and he discovered the galactic center. I think it was off by 10 arc minutes originally. But he did it with a single pixel. So he took a pixel and scanned it across the region. And you can still find his notebook, a picture of his notebook that shows the signal going to a peak and then going down as the pixel was scanned across the galactic center. At about the same time, George Ricci and Frank Lowe were doing similar work and made maps of the galactic center in the infrared. And some of you might know George Ricci. For many reasons, he wrote an excellent book that's in our lab that I asked students to read. He also is the principal investigator of the mid-infrared instrument, at least the US principal investigator for the mid-infrared instrument on JWST. And Frank Lowe spun out his infrared technologies to a company called IR Labs, which then got spun out into Universal Cryogenics. And so some of you might have used their equipment. We use it quite frequently. So they also mapped the galactic center. And Becklin and Neugebauer were at Caltech, and Ricci and Lowe were at Arizona. And that's a frequent competition in astronomy. It's Caltech, or more broadly, California versus Arizona. And that crops up over and over and over throughout history. Back in the radio at the National Radio Astronomy Observatory, Bruce, Balick, and Brown did further radio work using a 3-telescope interferometer with much higher resolution than what Jansky was using. And they found a compact object, a point of emission within that Sag A object, and they called that Sag A star. In fact, I think Brown called it Sag A star in a later paper about 5 years later. So then there was a big burst of activity, I would say, in the 80s with the advent of new detector technology. Gene Serabin and Lacey made observations over a number of years of the gas near the galactic center. It turns out that there's gas in the shape of a spiral. And by measuring the velocity, they were able to reconstruct an orbit for the gas and infer a central mass of 3 to 4 million solar masses. And they thought that that was a black hole. Now, at this point, you might be scratching your head because you don't see Genzel and you don't see Ghez, but all these observations really were leading up to the realization that there's a black hole. And in fact, you see in the 80s, Gene Sarabin and Lacey were talking about a black hole. That was the Berkeley group. And incidentally, Charlie Towns was at the Berkeley group and Reinhard Genzel was there too. Eventually, Reinhard went to Germany, and here is his first publication using individual stars, not gas, but stars, to infer a black hole mass of 3 million solar masses. It's in green because I put it in green because this is the work that relates to the Nobel Prize. A few years later, Andrea Ghez repeated that experiment with the Keck telescope. So Reinhard was in Germany. He was using the European telescopes. Andrea was at UCLA, which is where I was at that time, and she was using the Keck telescope. They did identical experiments. And so Andrea confirmed the German result and got a similar answer. So fast forward a few more years, there's Rainer Schottel. And here you don't see Genzel or Gez's name, but in the et al., Reinhard's name is in there. So that's the German group. And what Reiner did was he measured the individual orbit of one star. And all you need is one star. If you know a complete orbit of one star around the central object, then you know the mass of the central object. And here the result was 4 million solar masses. And then Andrea Ghez confirmed that a year later using the same star and got roughly the same result. And then Gillison, also in Genzel's group, found a similar answer, 4 million solar masses. Genzel went on recently to publish the gravitational redshift of S2, showing that there's a very strong gravity field at the location where S2 makes its closest approach to the central object. A year later, Andrea Ghez confirmed that gravitational redshift, and Abitur et al. Saw orbital precession of S2. So I'm going to explain more of this as I go along, but I'm just giving you a history showing you that the bullets here in green refer to the Nobel Prize winning experiment that most people think nailed down the fact that there's a black hole in the center of the galaxy. And it's funny, I've bumped into Gene Sarabin before, and he was sort of chuckling slightly in jest, saying, "Oh, the black hole, they found that again. Didn't we discover that in the 80s?" But the point is that using actual stars instead of gas is thought to be a more robust way to infer the mass. So how do you measure mass for orbiting objects? So first you find one object orbiting the other, and then measure the position versus velocity. So for instance, if you wanted to know the mass of the sun, then you could identify something orbiting the sun, like the Earth, and then map its position versus time to get its velocity. And then you can just plug it into some equations to get the mass. It's as simple as that. You're just using Kepler and Newton. So let's go back. This is 400 years, I guess. What did Kepler say? He said the orbits are ellipses, nearly circular in many cases. Equal areas are swept out in equal amounts of time as an object orbits its central star or central object. And the square of the period is equal, well, it's proportional to the cube of the radius. So these are Kepler's 3 laws. That was 1610. And then Newton came along and he had his laws. And so the first one is objects remain in motion unless there's a force that perturbs them or makes them do things. So a planet would simply drift with constant velocity in space forever unless it was near another object, say to tug it gravitationally, and then the planet would orbit that other object. The second one is force equals mass times acceleration, so that's F equals ma. And the third is force exerted by one body is equal to the force on that body. And gravity is proportional to the product of the masses divided by the square of the distance. That last one is Newton's law of gravitation. So these are very simple, and they're things that presumably you would learn in high school, I guess, high school physics. And so let's combine that high school physics with this middle school math. I think in the abstract, I'm not sure if I said this, but I said something like the math that was used to get this Nobel Prize was high school level physics. And then when I wrote down the math, I realized it's more like a middle school math. So it's very straightforward. So here you can see we're using one of Newton's laws, F equals ma. And that's a very general equation. It doesn't have to only apply to an object in circular motion. But if the object is in circular motion, then you can convert the acceleration a into v squared over r. So v is the velocity of the object going around in a circle, and r is the distance from the object to the point about which it's revolving. Now, in the next part here, I moved r to the front, and then v I converted into distance divided by time. That's what velocity is, distance divided by time. So the distance of an orbit is pi times diameter, and the time is t, capital T, which I'm using to symbolize the period, the amount of time it takes. So for the Earth, it's pi times the diameter of the orbit divided by t is 1 year. Okay? And we can convert diameter into radius, 2 times r, rearrange terms, and you get this equation. So what this does is it tells you the force on an object in circular motion around another object, and it can be expressed in terms of the radius of the orbit and the period, capital T. Now we can use Newton's law of gravitation. So when the force is due to gravity, it's equal to capital G, which is the gravitational constant, times the product of the two masses divided by the distance between them squared. So you have the force of something in a circular orbit at the top, and then in the second equation, when that force is due to gravity, you can use this expression. So you can equate those two. So you equate those two, and then you can solve, if you want, you can solve for the period. And actually, this is Kepler's law, where the period squared is proportional to the radius cubed. A more complete derivation would lead to this expression where the mass is actually the sum of the two masses. But if one of the masses is really big, then it reduces back down to this. So take the case of the sun and the earth going around the sun. In that case, the mass of the earth is insignificant compared to the sum. So you don't need to consider the mass of the earth at all. But now if you look at this, you can start to see maybe there's a way to calculate mass from this equation. And here it is. Mass equals constants times distance of the orbit cubed divided by the period squared. So all you need to do is figure out the radius of the orbit and how long it takes for the thing to go around the central object. That's it. And you can estimate the mass. And in fact, here's the answer for the Earth and the Sun.
Are you familiar with Jim Houck's version of your equation there?
No.
MP squared equals A cubed. Military police equals arrest. It's as simple as 1, 2, 3. It's got Kepler's law plus Newton's version.
I've never seen it. I'll look it up.
Military police equals arrest. As simple as 1, 2, 3. It's easy to remember.
It is. Yeah, I never liked capital T for period, but so if you put in the distance between the sun and the earth, which we usually call an astronomical unit, 1 AU, and then you put in a period of 1 year, which is the period of time it takes the earth to go around the sun, you get a mass, and it turns out it's equal to the mass of the sun. So it works, obviously.
Yeah, the Jim Houck version, the mass is in solar masses, the period is in years, and the semi-major axis is in AUs.
So everything is 1, 1, 1.
Yeah.
Yep. So I redid this calculation, and I put in R equals 1,000 astronomical units, and the period equals 16 years. Now you might wonder, why in the world would I choose those numbers? Well, those are the numbers for the star that comes closest to the black hole in the center of the galaxy. Those are the numbers. And when I plug those in, I get 4 million solar masses. So we just did the experiment that won the Nobel Prize. This is the math. And that's basically it. What we did,
1, 2, 3.
we didn't do the observations, right? And that's why they won the Nobel Prize. It wasn't for this math, because this math was developed 400 years ago. The other thing you could do is convert that to a density. If you know that the material that causes the gravitational force is confined to within a small radius, then you can put in that small radius. It turns out that the matter is confined to at most 1/10 of an astronomical unit for the black hole in the galactic center. When you stick that number in this density equation, so 4 million divided by volume, you get 10 to the 25 solar masses per cubic parsec, which for most of you, I realize you might not have intuition about what that means, but it means it's super dense and no one can figure out a configuration of matter at that density that would not be in the form of a black hole. So you measure the mass and then show that it's confined to a small volume. So that's it. Now I'm going to explain more about the actual experiment. So in the experiment, what you need to do is take pictures of the stars near the galactic center. Repeat this for 20 years. And then you'll notice that the stars move. Not all the stars, only the stars that are really close to the center, they move. You can supplement the data with spectra, and the spectra can give you Doppler shift that can give you another component of velocity. You need an independent measure of the distance to the galactic center to convert the angular motions to motions in physical distance, right? You need to know a distance in order to convert angles into actual physical distances. So with this, you can determine the orbits of the stars, and then you can estimate the mass inside the orbit. So that was the experiment. And if you look at this, it looks like the thing that takes the longest is bullet 2. You have to do this for 20 years, and then at the end, convert it to density, and then compare that to the density of the black hole. So here's a picture. This is a real picture of the galactic center. This is roughly the central parsec. So what do we see here? We see lots of points of light. Those correspond to stars. You see a bunch of blue ones and then a bunch of red ones. The red ones are dusty, and the blue ones are more like normal stars. And look at this yellow box here. That is a very small region. It's only 1 arc second on a side. And here's an inset zoom of that spot. And whoever made this put an X or a plus sign at the location of the radio emission, that compact radio emission that Bialik and Brown saw in 1973. It's thought that that radio emission comes from material falling into a black hole. And so that would be the location of the black hole. Here is the star S2. So this is one picture. It's a snapshot in time. And all you need to do is just repeat this for 20 years. Now, of course, a lot of technology went into making this happen. And of course, I'll talk about that. So here's an animation of the stars. This is reconstructed from actual data. Look at the date in the lower left. That's year. I think Genzel made this animation because there was some gas falling into the black hole, and that's the event that they wanted to simulate with this animation. But you can see the stars zipping around this central dot. See this dot here? That's supposed to represent the black hole. And look at the stars zipping around it. So those locations are based on real data, not in 2039 yet, but beforehand where you saw the orbits, it was based on real data. So yeah, you can see here year 2000. So these dots correspond to where actual stars were. And you can see from the blue lines, they're able to estimate the full orbital parameters for these stars. And therefore each star leads to, on its own, a separate estimate of the mass of the black hole, mass of the central object. Now, since they made the claim that there's a black hole and basically convinced everyone, they've also been able to measure relativistic effects, which is interesting because now you can use this as a laboratory to prove or disprove Einstein. And here's an animation that shows this star S2, and it's zipping by the black hole, and its color is shifting due to gravitation, something called gravitational redshift. And in fact, they measured this in 2018. So that was an interesting result. They've also measured relativistic precession, which is something that we can measure in Mercury's orbit. You can see that the orbit doesn't close back on itself, so it doesn't keep going around. the same line. It's actually precessing. It's elliptical and it's precessing. And this cartoon here is supposed to show the star S2 going around the black hole. And you can see that the axis, the major axis, is twirling around, going clockwise. So this is another relativistic prediction by Einstein, and it's been measured in the galactic center. So there are two relativistic effects. Now there's something else I just wanted to talk about because it's kind of entertaining. It's something called getting ripped. My students love this one. So what am I talking about here? Is it getting ripped off when you go buy something? Or is it SpongeBob? His pants are getting ripped. There's Patrick over there. Is it rest in peace? Or is it this guy's getting ripped because he's working out in the gym? But it's something else. It's called spaghettification. And this is a technical term used in the 70s. It was published. It's when your body is pulled apart into a shape of a thin spaghetti noodle as you get ripped apart and sucked into a black hole. And this happens because the force on your head is a little bit different than the force on your feet, just because of the slight difference in distance between the black hole in your head and the black hole in your feet. So it exerts a force on your body and it rips you apart. So when people learn about this, they tell me that if this had to happen to them, they'd want to arrange it so that they didn't get ripped apart until they went into the event horizon of the black hole. That way they could look around and see what was there. And maybe it would be worth it then if they then got ripped apart, but they wouldn't want to get ripped apart outside of the event horizon. So you can calculate the location of where you get ripped apart, and that delta F is the tidal force between your head and your feet. And you can invert that around and estimate the location, the rip radius, the distance from the black hole where you get ripped apart. And it's a function of how much mass is in the black hole. See that capital M up here? So for a solar mass black hole, you would put in one solar mass, and the answer would be 480 kilometers from the center. So you can re-express that in terms of the event horizon, which is the Schwarzschild radius. And so it's 160 times the event horizon, but then it depends on the inverse 2/3 power of mass. And so it turns out you get ripped up outside of the event horizon if the black hole's small enough. So you don't want to get stuck in a small black hole because you get ripped up before you even get the fun of going inside. So if you want to do this, I suggest you go to the galactic center, because then you'll be able to go into the event horizon and get ripped apart. But unfortunately, you can't tell us what you see because you can't get information out. Now, there are all sorts of effects around a black hole, and maybe you have even seen some of this in the movie Interstellar, which was kind of neat. So as the object approaches the event horizon, light gets shifted redward to the infrared, radio, and even undetectable as you get right to the event horizon. Time appears to slow down, and it would freeze at the event horizon. And the astronaut looking back at us, for them, they think time is proceeding normally. So their watch looks like it's normal, but they would see time running fast for us, and then light from us would be blue shifted. So, if you're going to do this experiment, this is what you should be expecting to see. Now, I'm going to take a little digression here. So I've explained to you the experiment that Reinhard, Genzel, and Andrea Ghez did over the past 30 years or so that led to the Nobel Prize. And I wanted to tell you a little bit about some of what I was doing at that time and how it related to the work that they were doing. So one of the problems is that the stellar images are really blurry as observed from the ground, and the biggest telescopes are on the ground. So if you go to use the Keck telescope and take a picture of the galactic center, it doesn't look as nice as the picture I showed you. In the picture I showed you, you saw all these beautiful point-like stars. And that picture was only taken with adaptive optics, and I'll explain that in a few seconds. Before that, they just had to take pictures and get blurry pictures and not be able to see the stars in the central arc second. Okay? So another thing that we were doing at the time was, instead of looking at the stars around the black hole in the central arc second that we couldn't see because it was too blurry, we would look at stars around further out. And there's a little statistical trick that you can use. And so here you see a pictogram that I put together of these rectangles. And these are just lines I overdrew on a picture of the galactic center that I took. And what it indicates is I placed a spectrograph slit at these locations and I took a spectrum at every location in this whole field, and then went back and extracted spectra of all these stars. Now, here's the principle. If you can't follow a single star in its orbit to figure out its orbital parameters, what if you measure the velocity of a bunch of different stars all at random locations within their orbit? You should be able to relate the velocity dispersion of all those stars to the mass in the center. And the nice thing about this is you don't wait 20 years, you do it in one day. You make all the measurements all at once. And then you take the standard deviation of the velocity of all these stars and then relate it to the mass using some sort of simulation. And this is what people were doing. This is what the data look like. It's very complex. I can't really explain this now, but this is the raw output that you get. And each horizontal line corresponds to light dispersed in wavelength from each of the stars along the slit as I was scanning it across the galactic center. This is a feature in the spectrum due to the carbon monoxide molecule that absorbs light from the star. And so what you end up seeing is this picket fence appearance. And it's easy to see when that's shifted. So see the thin line at the bottom here, the spectrum? See how this cliff is shifted with respect to the cliff and the upper plot. So the upper plot corresponds to zero velocity, and the lower plot is what I measured for a bright star, and it shows it's shifted. So it looks like this star is blue shifted, so it's coming towards us. So that's it. All you need to do is measure the velocity shift and convert that into, measure the wavelength shift and then convert that into velocity. So I did this for each of the stars, and here's a plot of the velocities of all the stars where the open circles correspond to velocities away from us, and filled circles correspond, filled is away from us and open is towards us. And so you can see it's kind of random. So a bunch of stars are coming towards us, a bunch are going away from us. And then you can use this equation here, which is the Binney or Bacall-Tremaine mass estimator. And this makes a bunch of assumptions. It says if all the test points that are going around a central object are distributed in a certain density distribution, then their velocity dispersion will be related to the enclosed mass, which is that m. So that's it. So you don't have to be concerned with the details. I'm just showing you can relate the velocity dispersion of all your dots to the mass inside.
Isn't that basically the virial theorem?
Yeah, so here's the problem. Exactly, here's the problem, Bill. That assumes a certain distribution of the particles, and it turns out that most of the particles used are old stars, and the old stars appear to be absent from the very center. So when you see the old stars that appear to be on the center, they're actually in front or behind the center. So they're not right around the very center. And if you look on the left, that's the distribution that the Bacall-Tremaine mass estimator assumes. On the right is the actual distribution. This is simulation, but this has a hole in it. You see this R naught 0.4 parsecs. There's a hole of the stars in the distribution of the stars in the galactic center. And you have to take that into account. And when you take that into account, you get this solid line, which is 3.5 million solar masses for the mass of the black hole. If you didn't know that, you would estimate 1.5 to 2. And the reason I'm showing you this is because early on, no one had complete orbits for any of the stars. Instead, people used this mass estimator, and they were wrong by a factor of 2.
But it still would be a massive black hole.
Yeah, absolutely right.
Millions of solar masses.
Yeah. The point I'm making here is that there's a hole, and so you can't use the Bacall-Tremaine. And then once you get individual orbits, it matches the simulation if you know that there's a hole. So this is a little digression that I just wanted to tell you about.
Did you then assert that there was a massive black hole at the galactic center from your data?
Yeah, but it was. I think it was too late though.
What date was that?
2002.
Okay.
So this is basically a historical footnote as to why everyone got the wrong answer for 5 years. And it's just because the Bacall-Tremaine distribution is not what actually exists in the center. Okay, so I want to talk about the technologies that really made this happen, because you see that the conceptual framework was put together 400 years ago. So why wouldn't you ask? Why didn't Kepler or Newton do this experiment? They wrote the equations, and the reason is because they didn't have big telescope mirrors, adaptive optics, or infrared detectors, three technologies of which came to fruition all at the same time in the early 90s and through the late 90s. So basically, Reinhard Genzel and Andrea Ghez were two people who had access to this technology to do these experiments. And I've written down some names of some people who developed the technology, and they're not all the people. These are some of the people that came to my mind, and I'll tell you a little bit more about this. And then instruments also were important. So big telescope mirrors. Jerry Nelson was at University of California, Santa Cruz. He's still, well, he was recently, passed away recently. And he had an idea that if you want to make a big telescope, you need a big mirror. But if you can't make a single big mirror at one go, maybe you could make a bunch of little mirrors and then stick them together edge to edge. And those little mirrors would act like a big mirror. The problem is they have to be aligned to within 100 nanometers or so. So they have to really be phased very finely. So this was his dream. Roger Angel wanted to make big single mirrors. And it turns out Keck used Jerry's design, and the Very Large Telescope in Chile used Roger Angel's design, as well as other telescopes used his design of single mirrors. So the Keck is a segmented mirror. And here you can see Jerry. And you can see, if you look closely, you see these hexagonal sections, 1.8 meters on in diameter, but altogether, the segments make up a 10-meter individual mirror when it's phased. By the way, this is a pretty big thing. It's misleading because Jerry looks so big, but here's a little humanoid figure here over on the deck on the right. So the Keck telescope got built, and it used that technology. Here's Roger Angel, and he's examining his mirror blank, 8-meter mirrors, and that's what the VLT uses, the Very Large Telescope. Now, these days, telescopes use one variant or the other. So take a look up here. These little hexagonal sections, this represents the Keck mirror. It turns out there are two Kecks, Keck 1 and Keck 2. And this little animation here, this cartoon, represents the two Keck primary mirrors. Let's see, let's take a look at down here. See these green ones? The Very Large Telescope. So the Very Large Telescope is actually 4 telescopes, 4 nearly identical telescopes. And each one uses an 8-meter mirror. So you can see in cases where it's the Arizonan people who are using individual mirrors, sometimes ganging them up, like in the Large Binocular Telescope. Look down here. Here are some future telescopes, the Giant Magellan telescopes. This is interesting. Look what they're doing. They can only make 8-meter mirrors, and they like single mirrors, but they want a bigger telescope. So they're taking a bunch of 8-meter mirrors and putting them next to each other to make one telescope. And of course, there are going to be gaps. Here's the 30-meter telescope, which has a bunch of hexagonal segments like the Keck. And then here's the European Extremely Large Telescope. We're running out of words here. Extremely large, and they're planning also to have a segmented mirror. And then look at the background here in gray, the Overwhelmingly Large Telescope, the OWL, but that got canceled because it was too big. And I saw recently, I don't know if you saw this in the news yesterday, there was an article about planning a big telescope on the moon. I think it was called the Ultimately Big Telescope. So adaptive optics were developed, again, by many people. I'm only talking here about Keck. There's also the whole German side, and also Arizona. Peter Vizinovich at Caltech and Claire Max, and there's Peter and his group celebrating a success implementing adaptive optics. And here's Claire Max at the Lick 3-meter telescope that I used for my thesis in 1995. As many of you know, hopefully, a point-like object in the object plane will produce an extended object in the image plane that has a shape like this for a circular aperture. And this is the intensity pattern. So there's a central peak and then some circular ripples. It's called an Airy pattern. And this is true if the optics are perfect. And here's a cross cut through the intensity pattern. You can see the secondary peaks and this is a log representation in the lower right. And here's what it would look like if seen in an image. And you can see if there are two objects near each other, if they get too close to each other, it appears that they're just one object. So this spreading of light in the image plane induces a criterion for how far away point-like objects need to be in the object plane in order to discern them. And that's called the Rayleigh criterion. And it's expressed this way, that the minimum separation equals 1.22 wavelength divided by diameter. So a bigger telescope, bigger D, will mean you can discern things that are closer together. And those stars near the black hole, the central arc second, are so close that you really do need a big telescope. But the problem is that the Earth's atmosphere does this. Okay, as the Earth's atmosphere passes through the beam of light, then the stellar object gets blurred. There's a way to fix this, which is called adaptive optics. And here you can see a cartoon animation from the Gemini observatory of an instrument that does this correction. And so you can see light coming in from the top, from the telescope, being expanded, and there's a sensor that measures the error that the atmosphere induces in the beams. You can see that the stars flopping all over the place. And then a signal goes to a wavefront corrector, which perturbs the mirror. And you can see the wavefronts coming here, they're perturbed. They look like potato chips. So they have wavefronts that are perturbed in some way. And that those perturbations are measured and fed back into the mirror, which then changes shape to counteract the potato chip shape. And then they come out as perfect planes. You see that? This is done tens of times a second. And what that does is it corrects the effects of the Earth's atmosphere, and you end up with a beautiful image of a star. So this is the way adaptive optics work. And this is a cross-section of or an overhead view of the adaptive optics system for Keck. And I'm not going to explain this, except that this had to be developed, and it took a long time, took a lot of money. It was very difficult. And here's the end result. Here's a picture of the galactic center, those stars. And then look when we turn on adaptive optics. So the stars got sharp when they turned on the adaptive optics system. And by the way, this is what it looks like at the telescope. At some point you say, please turn on the adaptive optics. And then someone throws a switch. And this is what happens. And it's due to this sophisticated system that could be done. So adaptive optics was perfected, and we could see the stars around the central parsec. There's another technology that's important, and it's using the infrared. And here's why we use the infrared. On the left is a picture of a piece of sky that contains the galactic center. And I always give this out as a challenge to my students. I ask them to point to the galactic center based on that picture, and if they can get it, then I owe them a beer. So it turns out they could never get it. And the reason they can't get it is because any star you see in this picture is not at the galactic center. It's closer to us. Because at optical wavelengths in the V band, where our eyes are sensitive, the dust between us and the galactic center absorbs the light. So we can't see it. So here's a relatively short exposure of the same piece of sky. Do you know where the galactic center is? So hopefully you know where it is. It's down here. So it turns out that only 1 out of every trillion photons from an object at the galactic center reaches us at optical wavelengths. But at infrared wavelengths, it's much more. 1 out of every 10 photons makes it through the dust. So we look at objects in the galactic center using infrared because we have to, because of the dust. So it's as simple as that. And I'm going to skip this animation. There's a neat little animation showing a journey to the galactic center. So here are some people who developed infrared detectors. Don Hall, who recently passed away, he was developing mercury cadmium telluride since the 1990s when that material system was being developed for Hubble NICMOS. Al Fowler was developing INSBE, and Judy Pfeiffer and Bill Forrest were also doing INSBE. Kadri Viral was in industry, and he was the lead at Rockwell, which became Teledyne. They're the ones who are the leader now in infrared detector technology, and it's mostly MERCAD that they're developing. Alan Hoffman is another character who is in industry, and he was a real friend of astronomy. He was sort of a deep down an astronomer who went into industry, and so he
worked at the U of R in a gravity wave experiment, and as a postdoc, and he had to get a real job, so he took a job at SBRC, and they were developing infrared detector arrays, and he recognized, oh, those would be good for astronomy, and he contacted Judy Pfeiffer and offered, well, we can supply you with some detectors if you can show us that you can actually do it, put them in a camera.
Mm-hmm. So that led to, frankly, that led to the detector that was in the spectrograph that I used, where I showed you the slits going across. I'll talk about that in a little bit. These are, amazing devices in themselves. On the left is a 4K by 4K detector from Teledyne with 10 micron pixels. And on the right, you can see pictures of the family of detectors made in Innsbruck from Raytheon. And one or the other detector was used in each of the instruments leading to the Nobel Prize, which leads me to instruments. This is a short list of some of the instruments that were used both in Germany and on the American side. Each of these acronyms stands for something, of course. Sophia is son of Isaac, which I thought was funny. And most recently, sphere and gravity are the instruments being used by the Germans to do the general relativity test. Some of these are imagers, some of them are spectrographs, and each one is painstakingly designed and constructed, and they're one of a kind. And these days, they tend to cost $10 to $20 million each. This is a ray trace of one of the instruments called NIRSpec. And I have this because I did this design. So I did this optical design and did these ray traces and then had the optics fabricated. The telescope's on the left, you don't see it. But these rays here come into the window. You can see the window here. The light comes into the window diverging, hits a flat diagonal mirror, and then hits a collimating mirror. And then the light's collimated, hits another flat, goes into a pupil where we put filters. And then the light continues collimated until it hits a focal reducer, which converts F15 to F10. And then that gets focused down to a place where it looks like the rays just stop at the top and the bottom. And that's because there's a slit here. Some of the rays that are located at the opening of the slit continue to diverge at F10. It's hard to see, but they hit a collimator. If you look down at the bottom here, you can see the collimator here and the other axis. The collimator forms a pupil on this grating, reflective grating, which reflects the light according to wavelength into a cross disperser grating. So yet another grating that then cross disperses the orders, which then collectively go into a 3-mirror anastigmat, which corrects for coma, spherical, and astigmatism all at once. And then you can see the focus on the detector. Look there. You see the colors separated. So this simulation shows that this is a spectrograph and it separates the light according to wavelength. So I'm just showing you this because I had some involvement in this, and you could look at ray traces for all those other instruments too. And here's some of the data that I took with it. So this is reconstructing an image of the galactic center, and the number at the bottom represents the velocity. So this is where I took the slit and covered the whole galactic center. And so I have a spectrum of every location in the galactic center. And you can see the gas zipping around. See the diffuse light that you see moving around? So that's the gas in the mini spiral that Gene Serabin used first to estimate the mass of the black hole.
Where is the AF star in that image?
Let's see.
It's south. It's about 10 arc seconds south of
that. This one?
No, I don't know if it's that one. I'm just telling you, it's somewhat south. Not that far south.
It's got to be this one. So this is IRS 16.
Could be.
Yeah, I'd have to look at a map. 13 East is, I can't remember if this is 13 East, but it is one of these.
I want to know what its velocity is.
Oh, well,
you don't have to tell me now, just email me.
Well, here here what I did was I subtracted the continuum. So you can see the stars. So did you see this? See how some of the stars pop up? So
Yeah.
if we can find out which one is AF and see where it pops up, then we could read the velocity.
Oh.
Okay, so a few conclusions. So it took 400 years for the necessary technology to be developed. There was no eureka moment. People often think you win a Nobel Prize, it's because, at 3 a.m. in your lab, you get a eureka moment and you figure something out. A lot of people participated. Only 3 people can win the Nobel Prize. And then this is a challenge to future researchers. What can you do with technologies coming online? No, we don't know everything. For instance, what's dark matter or dark energy? And then here's the equation for a Nobel Prize, at least this one. So it's basic physics plus technology, and then you have to use it to do some experiment. And the experiment might take a long time to do, but it could be conceptually simple. And just before going, I just wanted to show a picture, a quote unquote picture, actual picture of a black hole in a nearby galaxy, M87, using the Event Horizon Telescope. And I say a picture of a black hole, but really what it is, it's a picture of light missing from around the black hole because the black hole's sucking up all the light behind it. And so you see a dark hole in the center. So let me throw over to Justin Gallagher. Justin, are you there?
I'm here.
Okay, maybe you can spend 3 to 5 minutes showing a few slides on the project that you're working on that we're doing at RIT. How's that sound?
Yep, I'll just need you to stop sharing. All right, hopefully you should be able to see my screen.
Yeah, we can see it.
Yep.
Excellent. So as a follow-up, at RIT, we're working on some detector technology that could potentially be in next generation NASA missions. And so to start off, I just want to talk about what potential NASA missions in the future are we going to have, and what is NASA looking for? And so I always like to look at the Enduring Quests and Daring Visions roadmap that was released in 2013, before I even graduated high school. And in the roadmap, there's a few science themes that really guides the roadmap. And the first theme is to primarily probe the early universe, looking at the growth of small quantum fluctuations growing from seeds into large-scale structures. We also want to probe the ultimate fate of the universe and its origin, and this would be by looking at the forms of matter and the energy that govern the universe and mapping the growth of cosmic structures throughout its history. We want to detect and chart the warp space around distant black holes by detecting the ripples of space-time produced when they merge. Or by we, I should say, NASA wants to unveil the chaotic flows of superheated gas swirling around black holes. NASA wants to use telescopes as a way to look in the past at the full history of galaxy formation and assembly, from the birth of the first stars throughout the turbulent epoch of rapid growth to the galaxies we see today. We want to make star-by-star maps of nearby galaxies across the range of observed galaxy types. We want to decode their histories and understand how they acquired their present-day forms. We want to characterize the evolution of planetary systems. For example, like our solar system, understand how our solar system formed, the process of planet formation, and how the crucial transport of water to the inner planets in a solar system. We want to complete the reconnaissance of planets and planetary systems that include gas giants, rocky planets like Earth and Mars, ocean-covered water worlds, planets close to and far their parent stars. And finally, we want to directly image planets around their nearby stars, search for their atmospheres, and of course, we want to potentially trace life. And so for the detector technology we're developing at RIT, we're primarily interested in the last 3. To summarize, they relate to making observations of exoplanets, planets located outside of our solar system. And so the big question is, how do you even go about detecting life on all these exoplanets? Because of course, you can't send rovers and manned missions to at the current time with our technology to all of these exoplanets. So really all you can do is observe the reflected and scattered light from a host star that passes through the atmosphere of an exoplanet. And so when you're making observations of an atmosphere, what are you looking for that can help determine if there's life or any interesting features? And so what I'm showing here is simulated spectrums of atmospheres for different types of planets. For example, Earth-like planets, as well as Venus and Neptune. These are all simulated values from this paper. On the x-axis, we have our wavelength. And on the y-axis, we have a ratio of the observed simulated planet flux as related to the host star flux. And what I want to point out is you can see that this value is 10 to the minus 10. And so the star is going to be much, much brighter than the exoplanet you're trying to observe. In the spectrum, you'll notice that there are some dips. I will remind you that this light is passing through the atmosphere of these exoplanets. And so when it's passing through the atmosphere, you can find in the spectrum absorption lines or emission lines that relate to different molecules. And specifically, the molecules that are labeled here are known as potential biosignature gases. When you look at an atmosphere of an exoplanet, you have to discern what you're trying to find. What are you trying to measure? In our understanding of exoplanet formation, there is a great biomarker, or I should say, biosignature gas between the relationship of methane and oxygen. Primarily, there is a oxygen-methane redox couple, and the idea is that without the presence of life, it's not going to be, sorry, let me start again. The idea is that you can use your methane-oxygen redox couple as a compelling biosignature gas because of the short kinetic lifetime of about 10 years of methane in Earth's atmosphere. And so the idea is if you're able to measure both oxygen and methane, and you believe that the system has been in process for more than 10 years, it would be unusual to find just methane and oxygen unless there's some external force, which in this case would be life. Life would be the substantial source of potential waste gases that would modify an atmosphere's composition and cause a disequilibrium in the expected molecules you'd find. So to do all of this, you need to talk about, of course, the technologies. What technologies are we developing? And for future missions, next generation missions are going to need low noise and large format ultraviolet and optical detectors. Your large formats are going to be particularly relevant for wide field applications, such as the high definition imager for the LUVOIR concept mission, which I have an image of the LUVOIR A concept down below. The high definition imager is an instrument that's primarily designed for imaging observations of wide field areas. And then another concept mission would be the HABEX, Habitable Exoplanet Survey Observatory, sorry. And for this, low noise is going to be particularly relevant for these low light applications where you have your exoplanet, which is much more faint than the host star. And for example, the workhorse camera and chronograph, which are primarily going to be used for exoplanet observation and characterization, our detector technology could potentially see itself in that electronic system. And so what's important about primarily that read noise, that last one? What I'm showing here is I'm showing a table of telescope diameters for very faint objects for a signal to noise ratio of 3. And at a given quantum efficiency and a read noise, you'll need a required telescope diameter in order to achieve that signal to noise ratio. I'd like to point out 2 boxes. There's a red box at 80% quantum efficiency and 3 electron read noise. The read noise is measured in electrons here, or is shown in electrons. And this red box will require a 12-meter telescope. the reason I colored this box in red is because this box correlates to what you might find on some of our current telescopes for a typical CCD. For example, the Large Synoptic Survey Telescope has a read noise of about 4.5 electrons. Now, if you're able to get a low noise detector, say a sub-electron noise detector, you can, of course, significantly decrease the telescope diameter. And for a quantum efficiency of 80% and a read noise of 0, you'd only need an 8.3 meter telescope.
What's your integration time here?
Unfortunately, I don't recall. I apologize about that.
Yeah, I don't remember that either, Justin. I'm not sure, Bill. I'd have to look at the simulation.
So the important thing here is, do you want to build a 12-meter telescope, putting in detector technology we have now, or do you want to build a much smaller telescope with potential future developed technologies? And I think the difference is really, do you want to pay millions for advanced detector technology, or do you want to pay billions for a larger telescope and to launch a larger telescope? And so for the project detector technology, what you see here is the CMOS sensor that we're working with for our project. You'll see that there are 20 detectors, which are the colored squares in the middle. They're located on a chip carrier and integrated in a camera housing. Specifically, this picture is of the detector technology that we were able to get our hands on before the project, and this is more of a room temperature setup for a camera. The detector technology is very important. It's going to have low power consumption, which is going to be great for telescope observations in space when you have to really worry about how much power you're consuming and your consumables. This device has a small pixel pitch. The pixel size is about a micron, a 1.1 micron pixel. The device has high conversion gain. As a byproduct of making the pixels so small, the capacitance sense node is significantly decreased, which causes a extremely high conversion gain compared to other devices. Typically, you might consider a 10 microvolts per electron for a typical CCD, where for our device, we've measured up to 400 microvolts per electron. So each individual photon is able to make a large signal response. And due to that high conversion gain, we're able to get a sub-electron read noise. For this device shown here, we've been able to measure an array average read noise of about 0.27 electrons. And because of our small pixel pitch, high conversion gain, and sub-electron read noise, this device is both single photon sensing and photon number resolving. And so that's the detector technology. And to give a small overview to finish my talk, this is a list of our project milestones. Right now, we're nearing the completion of our milestone number 1, where we're designing and fabricating our readout electronics. We're going to follow it up by characterizing our device in the lab. So that's going to be in our cryostats under a vacuum. Then we're going to radiate the device with a proton beam to simulate what damage the detector might see in future missions in space. We're going to characterize the device, of course, after radiation. We want to mount a pristine device at a telescope and actually demonstrate our detector technology. And then we're going to take our current detector technology and redesign it with the understanding of future applications. And so I just want to thank you for giving both Don and I the opportunity to talk today. Thank you very much.
Yeah, thank you, Justin, and thank you, Don, for that. That was a very interesting presentation. There are some questions in the chat, so I'd like to give people an opportunity to ask questions.
I have the first question. Can I ask a question?
Go ahead.
Justin, what are you showing us?
Sorry. So this is an image that I took with the camera that I showed earlier. This is the RIT Tiger logo, and I put the logo on a wall set up our camera, and made the room extremely dark to the point where each pixel on average is able to get about 2 average photons per pixel. So this is a single image taken with our sensor, and you can clearly see our resolved RIT Tiger
Yes,
in a
I
low
guess
light condition.
I guess a couple things that are interesting is that one is the noise must be substantially less than 2 electrons if you can see the image so clearly. And the other thing is, it is possible to discern objects at just the 1 or 2 photon per pixel level.
Yep, the 2 photons here was just my test setup.
Okay. Chris, do you want me to look at the questions?
Yeah, actually, I'll allow people to jump in, unmute themselves, and ask questions themselves. So let's see, Rajesh, are you?
Yeah, I just unmuted my mic. So my question is, I've been reading about these new satellite constellations that, either Bezos or Musk or whoever's, or Facebook is launching into the sky. I'm seeing these pictures in the newspaper, these streaks, and I'm wondering, oh my gosh, what's that going to do to Earth-based astronomy? That question occurred to me while you were talking about adaptive optics and all that.
Yeah, so Elon Musk claims that they iterated on the design and they're painting them darker, they're painting them blacker. And so he claims they won't be a problem. The other thing is,
Well, if they paint them black and then they'll kill the infrared.
well, so if you look at the early images, they look brighter than they look eventually because they do get out further. So as far as the infrared goes, the real problem here, I think, is in survey missions like LSST that's going to map the sky, and then a substantial fraction of their images are going to be littered with these streaks, and they've been trying to figure out ways to remove the light. You can remove the light, but then you have to throw away some data. You have to write an algorithm that finds where these streaks are and then removes that data, and then you replace the data when you go back to that piece of sky and take another image. So it's a hassle. I don't know that it's a big deal, but there certainly are astronomers who say it's going to be a big deal.
Yeah, I got background in optics and signal processing, so I guess with all the signal processing technology we see in AI and everything, I'm just wondering if you apply enough SP to astronomy, you can perhaps achieve something, but it is going to be a pain.
Rajesh is saying, and what I agree with, he now works for L3 Harris. I started at Kodak, which turned into ITT, which turned into L3 Harris. And I honestly agree 100% with him. Stray light is a real problem. And it doesn't matter if it's close to you or far away from you. Those detectors that we're making now are so sensitive that they can pick that up easily. You're talking about a photon or 2 here and there. And that kind of sensitivity is going to get thrown for a loop if we don't start to lower the level of ambient light when there shouldn't be any.
There should be an international organization that rules on whether you can do this or not. Can I put up 10,000 satellites? And the answer might be no.
Yeah, but you don't have that same problem here on Earth when you want to build just 10 strip malls, and you've got
No, there'll be rules about strip malls too.
Well, yeah, exactly. But the thing is when you put all these lights up, it really plays havoc. And anybody that I grew up down in Allegheny County in New York. We used to go out and look at the stars with a naked eye. Couldn't do that up here when I came to college because there was too much ambient light. You could see some constellations, but it wasn't anything at all like what it was down there. And even now down there, it's not as good as it was when I was in my teens, that's for sure. So,
yeah, well, one thing you could say, I mean, there's certain parts of the Earth where, people are going to settle and cluster, but thankfully there are certain parts of the Earth where there is never going to be large population clusters. So as long as you're talking ground level, you can find some dark areas. The problem is when people start filling up the sky, that's the issue. And by the way, as a side note, the only reason I didn't turn on my video is because my lighting in my room is weird and you'll just see a glow around my head. So apologies for that.
So it sounds like you need that observatory on the moon then. We also have a question from David Lees in the chat. David, if you don't mind unmuting yourself, you can ask that.
Sure. I was just wondering, Justin, those well sizes are, I mean, the physical sizes of your pixels are pretty small. I mean, I think you said 1.1 microns. I was wondering what kind of well capacities do you have?
So yeah, great question. Unfortunately, we didn't measure that, but our collaborators on this technology at Dartmouth have, and they've measured that the well capacity is about 200 electrons for the photodiode. So it's very, very small.
So doesn't that play a problem? I mean, Jim was asking the question about stray light. So if you have a huge amount of stray light and your signal is, a part in 10 to the 10, you must be doing a hell of a lot of integration with those things.
Yes, so that's definitely a consideration, because you definitely need to read out these devices quickly. And so one of the items we're going to look at for redesigning the sensor is how to improve the duty cycle of the device.
Yeah, to get 10 to the 10th sensitivity, you need 10 to the 20th photons. That's a big number.
So Justin, I have a follow-up question. I'm just curious about the readout electronics that you said are being designed and fabricated. Is that being done in-house at RIT in the clean room there, or are you having that sent out?
We are having that sent out to be fabricated. Our students on our project are designing it and sending it off to be fabricated and assembled in with third-party companies.
Nice.
I don't have a question, but I have a comment for Don about the Nobel Prize.
Oh, yes.
Yeah, well, you just told us that Ghez followed Genzel. Genzel did it first and Ghez confirmed.
Yes.
Well, in fact, Genzel confirmed Serabin and Lacey.
Yeah.
I think, and I'm more familiar with Lacey. So since you can, I think it should be Serabin and Lacey and Genzel. If you've got to have a theorist, then I'd pick Lacey because he was the senior person on that project.
Yeah. Well, this is
Towns was the senior. Charlie Towns was the senior person. He was the leader, but he's not alive now, so he couldn't.
Also, he already had his Nobel Prize for the laser.
Well,
right?
that's not against the law to get 2 Nobel Prizes.
Yeah, I think one of the funnest thing to do is to play fantasy football with Nobel Prize winners. So I certainly like your lineup, Bill, and I guess people could argue for all sorts of other lineups. I mean, one thing that I'll tell you about what you just said is the person who did the most work of all people in the world on this project is Andreas Eckart, and he was second in command under Genzel.
Okay.
And he didn't win a Nobel Prize.
Yeah, well, that's the trouble with these projects that have huge teams, and who gets the credit? Everybody's important.
So I'll tell you a funny story. Reinhard pulled me aside one day and he said, I think you should go to Berkeley to be a professor there and work with Charlie Towns. And I want you to go talk to Charlie Towns. And I was being courteous. I said, sure. And so I talked to Charlie, and afterwards Reinhard said, okay, you're going to go there. And I said, this is when I had just finished being a postdoc. And I said, well, I just got rid of having a boss, and I don't want to have a new one. I don't want to be second in command, because that's what he was looking for. He was looking for someone to be Andreas Eckart and do this work that would lead to a Nobel Prize.
Yeah, well, he actually he gave Genzel Genzel was working there too.
Yeah, sure.
And he gave this project over to Genzel, the Galactic Center project.
Yep. Yeah, and then he took it to Germany.
Yeah.
So, I mean, obviously, for people who are in the field, they realize that it's not as if just the Nobel Prize winners are the only ones who contributed, and there are lots of other people, and they're really the figureheads in many ways, representing, such a great achievement, but it's not just them.
Yeah.
Are there any other questions from people in the chat? I know one thing I want to comment on. It's I'm really curious about all of the detector technology as well as like the optical systems, the mirrors, because Rochester plays a big role in all of that. And so I know I've helped fabricate a few of the mirrors, one at the Very Large Telescope, one of the corrector mirrors,
Oh,
when I was working at QED. One of our customers was doing that. And then I know locally here at L3 Harris, they can make large mirrors. And I've seen some of their equipment for 3.5 meter size mirrors that they can produce there.
yeah, they built the W first system, which originally was a spy telescope.
Hmm. What was that, Jim?
I think you're not supposed to say that out loud. You know?
Well, I remember when the news interviewed me when that happened, and I was talking about the spy telescopes and L3 Harris, and then they went to interview L3 Harris, and all they could do was take a picture of the reporter standing outside the building and talking about it because no one would talk about it.
Yeah.
I mean, actually, adaptive optics, it was pioneered by the Air Force in New Mexico. They're the first ones to pursue it. Likewise, infrared detector arrays.
Yep.
They're building them for the Defense Department.
Yep, I could have gone one layer deeper on all this and gone right back to the military for most of it. And
they had all the money. Come on.
yeah, I mean, the TMA, that 3 mirror and a stigmat, the TMA and NIRSPEC that I told you about, the optics.
Oh.
That was designed by Brian Zellers, who was at SSG in Waltham, and all of his work was designing TMAs for the military. And he used to tell me about all the TMAs that are on orbit that I'll never hear about. And he used to say at the end of every presentation, he'd give his optics presentations. At the end of every presentation, he would say, "God bless Ronald Reagan and God bless optics." And then he would sit down.
Smart man.
Because it was all out of that Star Wars stuff.
Yeah, we did a lot of that at Kodak.
Yeah.
In fact, you've mentioned Keck in your presentation several times. Kodak was the ones that finished the surfaces on those two mirrors, on all of the segments of the two mirrors.
Oh, I see. So
we used ion figuring to do that.
Were the segments originally made at SHOT, but then finished at Kodak?
Well, they weren't finished at Kodak until the company that was supposed to finish them couldn't finish them.
Oh.
We had bid on the project, but we didn't get it. And then the one that did get it couldn't configure to the spec. So they asked us if we could do it. So they sent each one of those segments to us and we finished them.
Well, hopefully you increase the price a little bit just to show them.
Actually, they did that more or less. They didn't charge them much because it was a feather in the cap, so to speak. It gave us a lot of, because it wasn't a black project, we got to talk about what we do here in Rochester. And that was one of the first times that Rochester got an idea of what we were doing there.
Yeah. Yeah, the detector companies say the same thing, that when the detector companies get to do astronomy, they can have pretty brochures, and it actually holds sway when they bid on military projects. It's just really good PR.
Well, also the engineers are happy. They can talk about their
exactly
fruits of their labor.
Yeah. There's still stuff.
The Keck mirror sounds similar to the Hubble Space Telescope, where the one company couldn't do it
on the backup mirror.
Yeah, it's in the Air and Space Museum in Washington D.C.
Kodak took it down, and that was part of the group. We went down and put it up there, and it's not up there anymore. I'm not sure what they did with it.
Yeah, maybe they'll have it was pretty impressive.
Oh yeah, absolutely. Well, there was news here about another telescope that actually it was ITT at the time, not Kodak, but same group of people, finished for a government project, and now it's been repurposed.
Hmm.
I think it's the, what is it, the Nancy Grace mirror?
Oh,
Yeah, so that is W first.
Yeah.
Oh.
So that'll be interesting how they took a mirror that was designated for something that other, and then they changed the prescription on the elements and put it back together again, and now they're using it for something different.
looking up instead of down.
Yeah. Yeah, absolutely. Absolutely. Well, it's been nice, gentlemen. It was a great talk. Appreciate it.
Yeah, thanks, Don.
Good, super, thanks. I had a lot of
Yeah.
fun. Thanks, Justin.
Yeah, thanks everyone for joining us tonight. And Don, I'll make this the recording of this available to you in the next couple of days here.
Thank you, kind sir.
Great. Well, everybody, have a good night. Stay safe. Stay healthy.
Do the
And have a
same.
good Thanksgiving.
Okay.
Are we supposed to clap for the?
You too. Thank you. We'll
Thank
see you
you.
guys.